Okay, so before we go to the solution of problem number 2 in your module, let me first discuss why there is a need for the inclusion of additional diode and even the inclusion of your shunt resistance in the implementation of your half wave rectification. So originally we just have a single diode doing the rectification. So what's not so good about this is I'm going to try to trace again how the meter movement is going to respond based on there based on the two alternations of the input voltage. So during the first alternation, so current will come from there, and this diode is going to be forward biased, therefore the resistance is going to be very low. This meter movement is going to respond accordingly. So there, no problem with that. However, during the negative alternation, current will come from here, and this diode is going to be reversed biased. When we say it's reversed biased, doesn't technically mean that the two terminals where the diode is connected to is going to open. It only means that this diode is going to offer a very high resistance. And if it's doing so, if it's offering a very high resistance, that means it's limiting the value of current that will pass through the circuit to a very small value. However, no matter how small it is, it's undeniable that that current is going to pass through still on the meter movement. So there will be an effect. The effect is opposite that of the positive alternation, apparently. So there is an effect. No matter how small it is, it's there. It exists. So there. So this is now the effect we're talking about. So there. So I've exaggerated it a bit. Might not be that obvious. It depends on the relative values of the resistances and the input. However, what we're trying to say here is this is not going to be perfectly half wave rectified, which can be a little bit problematic because the fact that we have based our design and the computation of our multiplier resistor, the value of our multiplier resistance, to the formula Vm over pi suggests that we are basically considering a perfect half-wave rectification to which the meter movement is going to be responding to. So, in short, there is a little bit of inaccuracy. But, of course, that can be remedied with the inclusion of a second diode. And that second diode is going to form what we call now, along with the original diode, it's going to form what we call your instrument rectifier. And it's a better way of rectifying an input, a sinusoidal input, for it to produce half-wave rectification. So how is that so? So again, we're going to trace now how the meter movement is going to respond when a sinusoid is tapped across its inputs. So a sinusoid again has two alternations, positive and negative. So we start with the positive. So current will come from this terminal. It will meet a node and it will choose to pass through either branch. And looking at this diode is actually forward biased, right? For this direction of current, this diode is forward biased. Therefore, it's offering a very low resistance. This diode is reverse biased, so it's offering a very high resistance. So current would choose to pass through paths of least resistance, right? So it will pass through this branch. So it's going to pass through the meter movement, most of it, and the meter movement is going to respond accordingly. So no problem with the positive alternation. It's the same case as that of your original circuit. However, for the negative alternation, wherein current will pass through here, it is going to meet that node, and from that node, you now have again two paths, and from those two paths, this time this diode is forward biased, and that diode is reverse biased. What does that mean? This diode therefore is offering a relatively low value of resistance compared to this diode. Therefore, most of the current will choose to pass through this path. There may be some which will pass through the other path, but most current will pass through this branch, which means to say we will be able to clear out this unnecessary portion of the waveform to which our meter movement is currently responding to. So if by any chance we did that efficiently, then there will be an improvement in our rectification. So this is going to be much closer to a perfect half wave rectified waveform compared to this one there. And some instruments may include a shunt resistance to be connected in parallel with the meter movement. For that case, that is to decrease this time the resistance as seen from the terminals, these two terminals, or basically the terminals of the source. So you are decreasing the total resistance when you are connecting resistances in parallel. Say, if this is 100, this is also 100, total resistance becomes 50. So total resistance decreases. If you decrease your total resistance, you are therefore allowing higher value of current to pass through the circuit. And why is that important? Because especially during the forward biased condition of the diode, if higher current passes through it, it's going to operate in a more linear manner. So as if it were a resistor. So cut the story short, the shunt resistance is used to decrease the total resistance to increase the value of current, allowing the diode to operate in a more linear manner. So there. So from there, we can now check our second example wherein it's asking us to solve from, aside from other things, mainly it's asking us to solve for the correct amount of the multiplier resistance. Oops, sorry. So there. So this is now how our circuit looks like. So it has an instrument rectifier. It has two diodes. We will be placing here a multiplier resistance Why? Because we want that if we are measuring here 10 volts AC, we want the current passing through this meter movement to be the full scale current, which is 100 microamperes. Let me emphasize that this current is in DC. It was also said that this meter movement has a resistance of 100, as well as this shunt resistance also has a resistance of 100 ohms. Now, this should be very simple. However, due to the fact that we have included here a shunt resistance, there is a little bit of a problem. And what is that problem? Regarding the formula that we have been using, I've been telling you this since the prelim, that SV is just simply equal to the total resistance. It's just simple Ohm's law. In fact, this is the formula that we used in our first example. But this is only valid because the total resistance is solved using the range to be the total voltage and the sensitivity to be the reciprocal of the total current. Now let me just remind you that since this is Ohm's law, this is valid. However, for this circuit, the 100 microamperes is not your total current anymore. So we have to be careful with how we're going to apply this formula, SV is equal to RT. However, it's not going to be that difficult because we can simply redraw this circuit because, again, going back to my previous example, I also emphasized there that the total resistance we're talking about here is the total resistance during the positive alternation. So I can probably redraw the circuit during positive alternation. So during positive alternation, then this is the current. This one is going to be reversed biased, so open, and this one is going to be forward biased. It's not approximately short because it has a forward biased resistance. That's why I would like to redraw the circuit. So this is RS, and this is now the forward biased resistance. What's the forward biased resistance? I believe it's 50. This is open, so we actually don't need to draw that, but I just placed it there. It's raining. Sorry. Is it noisy? I'm using a condenser mic, so you might hear a little bit of noise. I don't know, because this is a loud mic. Anyway, so this is 100 ohms. This is also 100 ohms. There. So this is now the equivalent circuit during the positive alternation. There. And again, what we want is when we are measuring an input voltage in AC which is 10, then the current which must pass through our meter movement, it should be 100 micro. However, that's a DC current, or meaning the average value of current, if it's ever in AC, the average value of current that may pass through our meter movement must be 100 microamperes for this to deflect full scale. So we have to solve for the total current first here before we can now solve our sensitivity. How do you solve for that? We can probably do KCL there, but before we can do KCL, we must know first the value of current at this branch. Let me label that as IX. So IX is equal to I don't know. For me, this is just common sense already, because these two terminals must be of the same potential as these two ones. So whatever the voltage here must be the voltage here. See, the voltage here, okay, I can write the equation for Ix so that you don't get confused. The voltage here is 100 micro. And that must be multiplied to 100 ohms. That's the voltage, which is the same as this voltage. To solve for current, it's voltage divided by resistance. So divided by 100. So Ix, in short, should also be equal to 100 micro. And total current, KCL at this node, will give us an equation for our total current equal to Ix plus 100 micro, or simply 100 micro plus another 100 should be 200 microamperes. Okay? Yep. This is in DC. So if we now take the reciprocal of that, then we probably are obtaining our DC sensitivity already. Oops, sorry. 1 over IT, but IT there is in DC. So this is 1 over 200 micro, which is 5,000. So our sensitivity is 5,000 ohms per volts per volt. AC sensitivity is 45% of that. So what is 45% of 500 or 5,000? It must be half of 4, 5, 2,250. There. So we have solved already for the two unknowns. Lastly, we need the multiplier resistance, the most important one. So AC sensitivity is 2250. Voltage is 10. And this must be equal to the total resistance. So what's the total resistance? We look here, it's RS in series with 50 in series with a parallel combination of 100 and 100. So RS plus 50 plus 100 parallel 100, which gives us a value of RS equal to, let me get my calculator, 2250 times 10 minus 50 minus 100, 150. Yeah, it's 22,400. Okay, so the required multiplier resistance must be 22,400, so that the meter movement is going to deflect full scale if it's measuring 10 volts AC. Okay,